Hello, everyone. I'm Han, and I'll be presenting my biomedical engineering senior design project that I've completed in a team of 2 with Jonathan Lee. We were advised by Professor Nia in the Nia lab, and our project is titled Probing High-Frequency Ventilation Using Crystal Rib Cage. And I know that has a lot of terms, and that's why I'll start with some background to make some things more clear before I start. So ventilation is simply the medical term for breathing in and out. And artificial ventilation is something we've sadly all became more familiar with during COVID. It's basically when someone's lungs are not strong enough on their own to keep ventilating themselves. So an additional machine is added in clinical setting to help them with that. And there's a specific type of artificial ventilation called high-frequency ventilation, which how that works is, so normally when we breathe in and out, we have these individual smallest air pockets in our lungs called alveolus, or alveoli as multiple. And they expand and contract. So if you can, and that's the way it works in artificial ventilation, in simple artificial ventilation. So if you think of that as a balloon, for each breath, it expands fully, inflates fully, and then it deflates. And the surface of the balloon has all the biological systems that allow the oxygen to enter the blood. But in high-frequency ventilation, instead of 12, 18 breaths per minute, they use almost 150 breaths per minute, so way faster. And what that does is instead of inflating that balloon, it almost makes it vibrate and keeps it inflated, but still allows airflow to go through that. And why that's important is this is used specifically in premature babies, where you don't want the lungs moving that much because they're still developing. In surgeries, where the surgeon has to operate around the lungs, so you don't want the lungs moving again. And in intensive care patients, where there's a risk of the lungs getting injured. So, there's a setback with working with the lung and those alveoli when you're working at the alveolus scale, though. And that is the current methods we have in the medical setting, like CT, MRI, things we're all familiar with. They don't have the resolution that we need to image individual cells, yet alone the alveoli. And there are alternative methods like microscopy where you can section the lung, that's called histology, and stain it and look at it under the microscope. But in that case, you lose the functionality. You can no longer make the lung function, so you can observe it under its natural state. So the Nia lab has developed a system called the crystal rib cage, which is basically a housing where you can put a mouse lung inside, keep it really close to its natural state, so like humid, and attach a ventilator to it, keep it ventilating. And since the rib cage is made of a gel coating that would allow the lung to move and a transparent plastic material that allows us to see inside, we can then approach that with a microscope and look at it. And as it's functioning. So how that looks is like that. That's a mouse lung being ventilated, and that laser is from the microscope. And what we see from that is something like this. So each of those air pockets are the alveoli, and you can see them extracting and contracting. So I'll move on with what our goal was with the crystal rib cage, what we wanted to do with it. So basically, we wanted to observe the lung under high-frequency ventilation. But we wanted to observe a specific thing called the phase lag. And what that is so when you ventilate the lung, you send in air particles into it, and how that would look if we were to plot the ventilator movement across time, it would look like something like this. And then the lung takes a second to react to that, and then it expands. And if we were to plot that, the pressure of the lung next to this, that would look like this, because there's a slight delay, because the lung takes a second to react. And if we look at it across multiple cycles, that looks like 2 curves like this. And the phase lag, phase shift, same thing. That's what that difference between them is. So that's just the mathematical term for that delay. And if we then calculate this delay at faster ventilation, slower ventilation across a range of frequencies, then we get to plot the phase shift across frequencies. And why that's important is because this is called the frequency response of a system. In this case, our system is the lung. And what the frequency response of a system tells us is basically the question of how does the lung behave at different frequencies. So this gives us key insights of the material properties of the lung, but it also tells us about how it would function in things like high-frequency ventilation, where it's not the natural state of the lung anymore. So as I mentioned, that's important to understand the lung better, but also most of our understanding in this field is based on computational models right now. And what we're doing here would be bringing observation-based methods into that setting to validate what we already have or challenge it to make improvements to it. This would also improve clinical applications like high-frequency ventilation, because we can get to see how the lung potentially gets harmed, or like how we can improve that process in medical conditions like high-frequency ventilation. Sorry. I'll move on with the methods that we used for this. So I've kind of mentioned this, but the lung is in the crystal rib cage. It's connected to the high-frequency ventilator. A piezo is simply an electrical device that vibrates really quick to push the syringe in and out. So that's basically our ventilator. And we had a pressure sensor monitoring the pressure at the entrance of the lung, which is that second curve that I showed you. So this is how we collected that. And then we could approach it with a microscope, which would give us something like this. And then we developed certain computational models to calculate from those images using MATLAB and AI software called Imaris to get something like this, where the software automatically detects the outline of the alveolus, like single alveolus, and then plots its diameter across time. So this would give us an additional curve of not just the pressure of the lung, but how the alveoli act as like they expand and contract, which is a different lag than the overall reaction of the lung. So we're looking at the lung response, but also the individual alveolus response. So I'll move on with some results that we got from this. I'll start with that pressure sensor data that we got. So here you can see, these are two comparisons of the two curves I've showed you in the first methodology slides. The top one compares their amplitude, which is just the top to bottom scale of that. And the bottom one is that phase shift, phase lag that we have. So we've seen an increasing trend with the phase shift as frequency increases. And we saw this interesting peak with the amplitude ratios as we approach higher frequencies. And then we repeated this with a higher ventilation amplitude, meaning that we pushed more air into the lung with each cycle. And it was a similar pattern. So this was not really amplitude dependent. So to further comment on these data, we need to compare them to other data that we collected with just our system that we used, because anything you use in this system has its own frequency response, and you need to know those first before you can comment on the lung. So here you can still see those two curves over there, the lung ones at two different amplitudes, here as well. And the others are a bunch of versions of the system with different parts added and taken out to compare it to. And what we see mainly here is the base ones, the linear ones, and the bottom one in the top graph are the system with nothing in it, so just the system we used. There wasn't much of a response. But then we also tested the system with air volume simulating the compressibility of the lung. So compressibility is just one of the many mechanical properties the lung has. It just simulates that air being compressed, like if you would take a syringe, close the end of it, if you push, it would push you back, so that like something like that. And the lung response was slightly different in the phase shift and significantly different from that in the amplitude ratios, which tells us that this response of the lung does not come from its compressibility simply, but probably comes from some more complex mechanical properties it has, like viscoelasticity of it. And then I'll move on with the results we got from that second part I've showed of image analysis. So here are some example images at different frequencies, and you can see it. We were able to gather that data across a broad range of frequencies and track it successfully, which was a goal of ours. And then you can see plotting it at a lower frequency and a higher frequency. There was more noise in a higher frequency, of course, because this is a much smaller time scale that we're looking at. But we were successfully able to plot it at different ranges. And then when we plotted it across frequencies, it was a lot of variability in data. So this is similar to that bottom graph in the previous graphs, but this time with alveolar diameter. It is difficult to make any comments on this because there was a lot of variability, but that's also a finding. We saw a lot of, like, the individual alveoli were not acting, responding to this frequency similarly within the same lung. So just to gather these conclusions together, with our first goal of quantifying that pressure frequency response, we were successfully able to plot it for the range of frequencies that we aimed for, and we were able to compare that to the system response as well, the system we used. And then with our second goal of that imaging part, we were able to design the pipeline for quantifying those diameter values across time. We were able to plot that on top of the ventilation curve, so we were able to time match those. But we still need improvement because we need more repetitions, and we might need to increase the magnification, so zoom in more to the lung because it moves really small magnitudes at the highest frequencies. And the future steps would be to optimize it for the higher frequencies, and also in the future to repeat this with diseased lungs to see how disease changes the response of the lung. Thank you. I can take questions.
Any questions for Han?
Was there anything that surprised you as you were going about this process, something that really shocked you when you came to a conclusion?
Well, there were a lot of parts. But there were a lot of parts with the process that I have not worked with such high frequency. I've worked at this lab before, but we worked at the natural, biological breathing rate, breath rate. And when you increase the frequency a lot, you see a lot of things, unexpected things from the system that you're using itself. Well, that's why we had to return and do all those measurements with the system itself. So I think that was the unexpected part, because we had a lot of back and forth with my PI as well about how we need to test even the smallest part of tubing we add to it, and seeing how much it impacted it was really interesting to see. That was a lot of cool physics in play.
Great presentation. I was just curious, what are the implications of alveoli responding differently within a lung?
With different alveoli within?
Yep.
I mean, it's difficult to get medical conclusions from that, the things directly relevant to the medical field. But one implication is that many computational models that are in use, that we already have and that we base our insights on, assume the alveoli to be acting similarly. Because you need to simplify the lung a lot to make mathematical computations like that. So they assume each alveolus to be a sphere that has an entrance where the air goes in and out. So that challenges the computational models we have. But we still need to do more repetitions to confidently say that there's a lot of difference across alveoli. Yeah.
Hi, Han. Great presentation.
Thank you.
In terms of the technology, how can you apply this to diseased lungs, and what can it tell you in terms of the disease, as well as diagnosis, treatment, or
Yeah. So that's what's good with the system that we have, because crystal cage, we can switch it in and out with different lungs really easily. And our lab currently has a lot of disease models like emphysema, different cancer types. So what they usually do is all these diseases constrict a portion of the lung, either constrict the whole lung overall, or a cancer could locally constrict a part. So my assumption is my guess is that would be changing, causing even further variability across alveolus.
I was going to ask the same question. Thank you for the presentation, Han.
Thank you.
Any more questions?
Hey, Han. Great presentation.
Thank you.
Can you see yourself working on this project in the future, post-graduation, do you think?
Well, I'll be staying in the NIA lab during my gap years while I prepare for MD PhD applications. So I will be working on this project further, and I'm hoping to complete those disease models and publish all these findings in a paper, hopefully.
All right, great job, Han.
Thank you.